If you don't use all the graph paper that I'm putting out on the desk, that's fine. I'll collect it at the end of class. But you need some graph paper for today, I would imagine. AJ, I have something from you that wasn't part of an assignment. Is it? Yeah. All right. So let's get started. So, is it not? Hey, let's look. Quick note about grade assignments and plan for Wednesday. I don't think I mentioned it yesterday, but Miss Estel has to teach a lesson for her stuff at UA. So tomorrow we are going to take a break from the unit that we're currently on because she's been planning for starting the next unit, but I delayed the test. So just be aware what Miss Estel teaches tomorrow will not be on the unit test, but I had to delay the test because y'all weren't ready, and we're going to go over some things today. And so I was planning on doing the test now on tomorrow or Thursday, and so I'm just pushing it back another day on Friday. So be aware what we do tomorrow won't be on the test. And I know it's like, well, Mr. Kenny, why are we taking a break? It's because Miss Estel has to do stuff for class. So just be aware of that. I did not get anything done grading wise last night because just being honest with y'all, my wife had a rough day yesterday. She's completely exhausted from taking care of Alex, and so I had to take care of him. Not I had to, but I took care of him almost all last night. So I'm trying to get those grades updated for those of y'all who have completed things late, stuff like that. But what we're going to focus on right now is how we can learn from the things that we struggled on. You'll notice that I did not provide any feedback on the understanding checks. One, I'm just using what I planned to do yesterday. I planned to give the understanding checks in the front half of yesterday and then go over them immediately afterwards. I have made scans of your understanding checks, and so that's how what I'm going to use to score them. So these understanding checks are yours. Even though I have not provided any feedback on them, they're yours to write on and take notes and do whatever you need to with them. So a lot of us should have pencils in hand or colored pencils out of the boxes to be able to take notes and notice what those new notes are more easily, things like that. We're going to go over the lesson 4, understanding check as an analysis, and then today we are starting the review packet that I've developed to help us prepare for the test. And we'll be mostly working in small groups for that. Hi JC, how you doing? You look scared. Okay. One of the things I will say is, again, one of the things I didn't put into the agenda that we are going to do is I'm going to go over a couple of details on the homework problems. Once again, no, I'll wait till then. But I need y'all to do homework. The vast majority of us did not turn any of that homework in. But I need you to do homework so I can see what we're struggling with so that I can give you feedback in class, things like that, right? So do your homework assignments. That's it. So here's that understanding check. Let's see if anybody had questions about 1 or 2. Specifically, I'm looking at the bell ringer for this. Number 1, how to know if it's equivalent. Okay. So some people did have questions about number 1. So when I look here, right, so the easy way to determine if these are equivalent is if we have a graphing calculator. We didn't have one yesterday. What can you do if you have a graphing calculator to determine if those functions are equivalent? You graph them, and what are you looking for?
If they map.
If they map to each other, right? But you didn't have to do that here. In fact, I was assessing a different skill. Can anyone explain to us what we could do for number 1 to determine which function is equivalent to what was given?
The little box thing.
Okay, I need a little bit more added on, Gabby.
You could distribute.
Okay, so we can distribute. I need a little bit more.
You could plug in your options into the little box thing, or the area, whatever it's called.
The area model.
And see if you get the same as the top.
Okay, so I think we're missing an important detail with that. We keep talking about the area model, we talk about distribution, but what are you trying to do?
Multiply.
Multiply. Thank you. We need to recognize that each of these forms is what type of form of that function.
Factor.
Standard and
So the answer choices are factored, right? And we need to recognize that because if it's factored form, what is the operation between them?
multiplication.
Multiplication. Like that's one of the things that we need to immediately notice. It's one of those things that, plainly put, it should not ever be a question. As soon as you notice, hey, that's factored form, the next thing you should think about is if I want standard form, how do I go to standard form?
Multiply.
Multiply. Multiply to get standard form. That's the concept here. If you have paid attention over the last couple months, I keep talking about the conceptual understanding and the procedural understanding. The concept here is to recognize that if I have factored form to get standard form, I'm going to multiply. That alone would have shown me pretty strong evidence of understanding. Notice I'm referring to that scoring rubric. I need to see that you understand the concept, hey, I have factored forms, I need to multiply to get that standard form. That's exactly what we did leading up to this understanding check yesterday. That's the concept. But now we need to put it in play. And so, what are the two methods we have to multiply? Distribute or the area model, right? The box, the area model. So, I mentioned it yesterday. There's a difference between what I personally prefer to do and what I think is best for students. Does anyone remember what I personally prefer to do?
Distribute.
Distribute. That's just because that's what I learned in school. That's what I practiced for the longest time. When I show you the answer or the work that I did, you're going to see distribution. Personally, I recommend the area model though. So here's the distribution that I did. I will point out, I did not finish any of the distribution until I got to part C. The reason for that, so please understand this is not complete, but when I did distributed 3x to x squared, notice I started from here and distributed this way, and that's totally fine. 3x times x squared is 3x cubed. 3x times 3x is 9x squared. 3x times negative 1 is negative 3x, right? So all of this in blue is distributing that 3x. Now I distribute my negative 1. Negative 1 times x squared gives me negative x squared. And I stopped there. I could have continued. Negative 1 times 3x is negative 3x. Negative 1 times negative 1 is plus 1. I will point out, you see how I line up my like terms? That's not something I talked about with Miss Estel, but I like to line up my like terms like that. It makes it easier to add and subtract in my opinion. Right, so when I distribute, I line up those like terms. That's your choice. You don't have to. But I did stop right here because what is 9x squared minus x squared? 8x squared. But what was this supposed to be? Negative x squared. So immediately I knew it was wrong, right? Like I didn't have to continue. I just made that note incorrect because that's 8x squared. It was supposed to be minus x squared, but I got 8x squared, I'm done. Right? It's incorrect. Didn't have to continue, I could have. Similar thing here, right? I distributed negative 2x squared plus that 3x squared here ends up giving me a plus 1x squared, right? But I needed a negative. And I continued until I went to C. Notice again, I distributed my x, that's how I got these three terms, distributed my -1, that's how I got these three, and I showed that it matches the standard form. Now, I saw a note from a student that, hey, I need to know how to use that area model better. And that's totally fine. So let's look at it. The one thing I didn't love about this question, but I also felt like I gave you all a good bit of time so that it'd be okay. You literally have to go through all 4 answer choices, multiplying to see which one works, right? It takes time, that's okay. Get an extra sheet of paper if you need to. But if I look at A, what I have is f of x equals x squared plus 3x minus 1 times 3x minus 1. The only thing that I would point out or note here before I use the area model, right? So distribution is what I have over there. To use the area model, so there's 2 different ways to multiply. When I do the area model, one of those sides is going to have how many terms? 3. And so it doesn't matter which way you orient it. We did talk about that in class yesterday. But notice I just draw a rectangle because what's on the inside of a rectangle? The area, right? And what's this called? Area model, right? Like that's why it's called that. I'm just looking at a rectangle and I'm looking what's on the inside of the rectangle. I draw my column and my row so that I can set up those terms there. Does anyone remember what I put in this top left corner? Multiplication. It's the operation that I'm using, right? I am multiplying, so I put that multiplication symbol in there as a reminder. Because I did this longer, I'm going to put my 3 terms here. Be careful. I saw some students who did not pay attention to the signs. This x squared is positive, right? This 3x is, but this 1 is, so I need a -1 here. You've got to pay attention to the signs. If you don't, it will mess you up. And then what do I need along the top? And I just draw in the lines to make it easier. And again, I just distribute. It doesn't matter if you start here and then go to here or here and then there. It's just you're multiplying. So what is x squared times 3x? What is x squared times -1?
-1x squared or -8 squared.
Either one, right? 3x times 3x. 3x times -1. -1 times 3x. And -1 times -1.
1.
And so I like to circle my like terms. And I will point out that this is where you also could have stopped. Because again, what's 9x squared plus -x squared?
8 squared.
8x squared. Do we need to talk about why it's 8x squared and not just 9, Madison?
You're all good, I realize.
Okay. Can anyone explain to me then, because I think this is something we did have talked about yesterday, why is 9x squared plus -x squared 8x squared?
Because you're adding negative, which is basically subtraction.
That's part of it, yep. What does this actually mean?
9 times x squared.
I need more.
9x times 9x.
I could see you thinking that. Be careful though, is that square on the 9 though?
No.
It's just on the x squared, so good thought.
9 times x times x.
Okay, you could see it as 9 times x. I'm going to focus on the idea that it's 9 just times x squared since I'm adding a -x squared. Because multiplication is repeated addition. So what does that mean I'm doing here?
Adding x squared 9 times.
There we go. Right? That's 9x squareds being added. That's what we would want to recognize. 9 times. And if I add a -x squared, that's going to create what kind of number? X squared minus x squared is 0, right? I've canceled out one of those 9x squareds that's being added, so how many am I left with? 8. That's why it's happening like that. When we add those like terms, we've got to remember the whole idea is that this coefficient is how many times I'm repeatedly adding. The coefficient is how many times I'm repeatedly adding. Repeatedly adding x squared 9 times and then taking away 1x squared. That's what's happening in the truest sense. Okay. So again, A doesn't work. You can look at C though. It's going to show it with the area model instead of talking it through all the way there, because I know some of y'all need to take some notes. So finish taking notes about whatever we just talked about, and I'll just write A or C up here. Why didn't you go before class? Do I have tissues out? Hold on one second.
I can't do it yet.
I mean, you can step outside without going to the bathroom. So while I'm getting these out, make sure you think through what questions you need to ask up to this point. Was it you who needed more than this? Alright. We're not divulging into chaos. What questions do you have about number 1 at this point?
About
Number 1.
you got them in different colors?
Yeah.
They both look like the same color, blue and purple.
Blue, purple, black, pink. Color coordinate things. And it helps me
Yeah, it's me too.
stay organized. Yeah.
How?
Teacher one day, she said that you had no black markers
Let me ask you a question.
Yeah, why would I buy a black marker?
So did you take, like how you did A, did you take C and do the same thing to compare it to the one we did?
Yeah, this is C right here, using the area model. I will point out, using C, notice this one I just did the 3 terms horizontally to show you it doesn't matter which order you do it in. But yeah, there's the work for C, and I believe that matches the standard form that we started with. What's your question, Salita?
I see where you got the 3x cubed and the plus 1, but where the middle one come from?
Okay, you understand how I got this negative 3x squared and 2x squared?
Yes, you did that one.
So what's negative 3x squared plus 2x squared?
Oh, I forgot you added.
You always add those terms. You always add your like terms. Questions, comments, concerns before we move to number 2?
No.
Okay. Oh yeah, so I don't think anyone asked a question about number 2. Let me check. Okay. So no one asked about number 2, but here is my answer for number 2. Which function has a 0 with a multiplicity of 2? Each root once, because the factor only once, right? So multiplicity of 1. I made that note for both A and B. Notice with C, that factor x minus 5 shows up how many times? So how many times will that root show up? Twice, so that would be the root x equals 5 with a multiplicity of 2. Here, the root x equals 2 is 3 times, so it would be a multiplicity of 3. About to move on to number 2, unless there are questions about that one.
And you did great.
I haven't graded it yet. I give it back to you so that you can take notes and learn from the things that you struggled with. But I will be grading them. Like I already see.
So you got, you see everything.
So I put it through a copier, it made scans of them, it emailed the scans to itself. So I have a PDF of everybody's understanding. Wait, was there someone not here yesterday? JC, you weren't here yesterday, right? That means she'll give me groups, and then I'm gonna do recess.
I'm gonna get it. I just did it. So that's oh yeah, you'll. My brother.
She says literally it's not, you're not in trouble.
The week.
Does anyone else need the understanding check because they were not here yesterday? Everybody else is good? Okay, no questions about number 2. Moving on in 5, 4, 3, 2, 1, done. Alright, number 3, I saw a lot of us who said, hey Mr. Kinney, I need help when it comes to graphing. I need y'all to remember the most fundamental piece to this. F of x and g of x are the what for m of x? Those are the factors. These are the factors. And it's critical that you remember that these are factors, because if you ever multiply by 0, what are you going to get? 0. Where do you see zeros on the graph?
X and Y intercept. I mean, X and Y axis.
X intercept.
Just x-intercepts. X-intercepts are where we see the zeros on the graph. Because literally, what is the y value? This point, if you find it, it's 5/3, comma, 0. This point, it does have an x of 0, but more importantly, it has a y of 0. Because I need you to pay attention. When we say f of x, the whole thing, is that an input or an output?
It's an
Input.
No,
That's an output.
Remember, x is my input, f of x is the output. So what we're doing here is we are multiplying just the outputs, which are also which variable? Y. We are just multiplying the outputs. That's what's happening in that dilation. So we are multiplying the outputs, so we are multiplying the y values. And again, when I multiply by 0, what do I get? 0. What property tells us that?
0 prime.
Oh, yeah. Now, this is the concept behind it. I wouldn't necessarily need you to write this detail out, but I want you to understand, right, when multiplying by 0, the result is 0. Again, that's the what property? 0 product property. And so we see these zeros, this is the important part. We see the zeros as what? Thank you. That's the whole point. We see those zeros as x-intercepts. So wherever I have an x-intercept for one of the factors, that's going to be an x-intercept of the dilated function. Hello? Yes, ma'am. Okay. Yes, ma'am. Anthony, you as well, sir. Alright. So wherever I see an x-intercept from a factor, that is also going to be an x-intercept for the final function. An x-intercept for from a factor will also be an x-intercept of the final function, because once again, that means I am multiplying by 0. That's the whole point.
Wait, where did you get the 3 from? I get where you got the 5, not the 3.
Where do you think I got the 5 from?
That's 5 of the 3.
Oh.
So, I will say this. You don't know that. I'm telling you, if you go through and you write the equation for this line, y is equal to, the y-intercept is -5, the slope is 3x, so if you solve for the x-intercept of 0, you get 5/3. I just went ahead and told you that. You didn't need that information. The whole point is, for that x-intercept, the y value is 0. So what do I need to do once I recognize those zeros, those x-intercepts?
Draw lines.
Your little dotted line section them off.
So I do a vertical vertical dashed line. Please understand, this is not a part of the graph. Again, this is just to help me stay organized. This is recognizing those zeros there. I want you to note, to the left of this dashed line, g of x is always what? It's always positive. It is also always decreasing, but more importantly, it's always positive, right? To the left of that dashed line, f of x is always negative, right? On the other side of this 0, g of x is always positive, and f of x is always
Negative.
negative.
It's below the x-axis.
It's below the x-axis, right? And then to the right of this dashed line, g of x is always positive, and f of x is always... Notice how it would switch from being negative to positive there? Where your zeros are the only places that a function can change from positive to negative or negative to positive. That's the only place. Because what's the number that is in between the positives and the negatives?
0.
0. That's the whole idea, right? That those zeros are in between our positives and negatives. So I draw the dashed line there to help me visually see where I need to be testing. And so when I look here, I know that I'm multiplying. So g of x is always positive. F of x is always, and what's a positive times a negative? Negative. So my m of x is negative to the left of that dashed line, but it's going towards what?
0.
The x-intercept, that 0. Right? So all of those are negative. Now I got to test similarly in between. Now, g of x here is positive, f of x is, so now m of x is negative. This is that special case where it's going to touch and then bounce away. Notice it never became positive. M of x was negative, and then m of x was negative again, so it's going to touch and bounce away. But at some point, it's got to start coming back to this 0, so it's going to hit a minimum and start to go towards that x-intercept. This isn't super accurate, but it is a rough sketch of what this graph would look like. Now, to the right of that x-intercept, g of x is positive, f of x is positive, so m of x is positive. There is m of x, or at least a rough sketch.
Mr. Kenny,
Yes, sir.
is it like ever possible for it to bounce off twice, like in combo x-intercepts? Like an M looking graph?
Well, so we've only studied quadratics and cubics for now, but, so, remember, what do we call these roots when it touches and bounces off? Those are called double roots. So that means that there would be 2 roots here and 2 roots here. So it'd be 4, so it'd be a 4th degree polynomial. We haven't gotten there yet. That's actually in our next unit. That's a good thought, right? So remember, the number of roots tells us what polynomial it is. Anybody remember what really important idea tells us that the number of roots matches the degree?
The fundamental theorem of algebra.
Fundamental theorem of algebra. Again, that's going to be on your test. You need to be aware of that. The number of roots, when you count with multiplicity, matches the degree. Okay. Any questions about this sketching now? Okay. One last quick note I do want to point out is this parabola, this quadratic, doesn't it have a double root right here? So m of x also had to have a double root right there. That's why that's happening, right? We don't see 2 functions going through there, but that is a double root for the parabola, so it had to be a double root for m of x.
Can you explain how it is a double root?
Ooh. Okay, so I'll point this out. I'm gonna go ahead and give you this equation. This is actually just the easiest quadratic that there is. It's x squared. So f of x is, no, g of x is x squared. If you look at f of x, you look at your slope and you look at your y-intercept, it's 3x minus 5. So m of x is equal to x squared times 3x minus 5. Okay? Remember, roots are also called zeros because the y value is 0. And this is again why we want to recognize that we have factored form, because I can use the zero product property. So 0 is equal to x squared. So literally that means that 0 is equal to x times x, or 0 equals x, and 0 is equal to x. You see how it showed up twice?
Yes.
That's why we call it a double root.
Okay.
Double roots also would be a 0 with a multiplicity of 2, right? You can have a triple root, which just means that 0 has a multiplicity of 3. That's it. Yep. Does that help clarify?
Yes, sir.
Alright. No more questions about number 3? So I actually wrote a good bit here. I will upload these slides and I guess the solutions that I created onto Schoology. If you want to go and look at these in more detail, because I show a little bit extra there. Number 4, so one of the things I want to point out is, I saw a lot of people here, I don't think anyone asked about number 4. We felt overall pretty comfortable with it. But y'all need to take note of this. I saw a lot of people say that part A has a multiplicity of 1. It doesn't have a multiplicity of 1, it is a degree 1. That's not what I was asking. The degree is 1, that is true. Right? 3x to the first. But I asked about the multiplicity of the zeros. So what do you need to identify first?
How many zeros?
Well, not just how many zeros. Don't you need to know what the zeros are? How can you tell me what the multiplicity of a 0 is without knowing what the 0 is? You literally can't. So the first thing you need to do is identify the zeros. I would write down that conceptually. Don't ID degree here. Looking for zeros and multiplicity. So first off, how am I going to identify what the zeros are? Yep, that's a big part of it, but what else? Don't forget the fundamentals. Why is it called a 0?
Because it's x-axis.
It is.
Value 0.
There we go. Right, so it is intersecting the x-axis, but the big part of that, because we don't have a graph right now, we just have this expression. The big thing is that means that the factors are set equal to 0, right? So don't ID the degree here. We're looking for zeros and multiplicities. So there's a good bit of work here, but notice the starting point for everything right here, and right here. What is the first thing I did for every single one of them? I set it equal to 0. I'm looking for zeros. And then I solved for my zeros. And then I identified the multiplicity. Multiplicity of 1 because the factor is there only once. Right? Only 1, 3x minus 2. X plus 3 equals 0, 2x minus 1 is equal to 0. I solved. There's my 0, there's my 0. Notice I said this is a multiplicity of 2 because that's x plus 3 times x plus 3. So how many times did that 0 show up? Twice. This is only 1, 2x minus 1, so it's a multiplicity of 1. Each of those with a multiplicity of 1. So if I'm asking you for multiplicities, you need to identify the zeros and then you can identify the multiplicities. Yes, Elijah.
So, for B. So I just added them.
Mm-hmm. So what is 3 for B? Not the multiplicities, the degree. There are 3 total zeros, but remember, multiplicity is how many times that 0 shows up. So when we say multiplicity, that is how many times each 0 appears.
So no, I mean not no, but so B got the multiplicity is 2.
For this 0.
So what about in total?
Well, but multiplicity is only how many times each 0 appears. So this 0 has a multiplicity of 2. This 0 has a multiplicity of 1.
You added them or the multiplicity?
Neither.
What?
This has a multiplicity of 2.
Uh-huh.
This has a multiplicity of 1. That's what we're saying.
So you're supposed to do it
Of each 0. Multiplicity is how many times each 0 appears. Notice I'm not asking you the degree, I'm asking you the multiplicity of each 0. Those are different. The degree is how many total zeros there are. I'm not asking you for the total number of zeros. I'm asking you for the multiplicities of each 0. Hudson.
But like for B, you necessarily have to find zeros, so I get where you're coming from. But if it's anything squared, it's repeated.
Yeah. But then how are you going to tell me what the whole point is the multiplicity is how many times each 0 appears. How are you telling me what the multiplicity is without telling me the 0? The whole point is that x equals -3, that 0 has a multiplicity of 2. Right? That's what I'm saying. Like, you have to tell me what the 0 is, and then you tell me how many times that 0 appears. Does that make sense? Okay? Should I create an example problem really quickly?
No.
Okay, there's at least one yes. So I'm not going to take forever on it, but I'll make a nice easy one. Okay. First off, I will point this out. What is the degree of this polynomial?
No.
It's 6-degree polynomial.
Right. Remember, I have 3 zeros here, right? Because it's cubed. I have 2 more here and 1 here. Okay? So that is a 6-degree polynomial. If you write it all the way out, when I say x minus 3 cubed, that's x minus 3 times x minus 3 times x minus 3 times x plus 2 times x plus 2 times x minus 3. Each of these are linear, so each one of these has how many zeros or roots? 1. So 1, 2, 3, 4, 5, 6.
So why you just add them with the right?
I'm going to talk about it. I'm about to
That's
talk
the,
about it.
that's the same root.
Okay,
Right.
good. So, this is an important detail. I will make this note. How many x-intercepts would this function have?
2.
Why do you say only 2? I heard 3 from several. Why do you say only 2, Anthony?
Because it's repeated, but it's the same number.
What are the zeros? What are the different zeros for this function? X equals 3, and x equals -2. Please be careful about this also. I need y'all to start writing your zeros as x equals blank. If you just write a number without saying x equals, that's not going to earn you full credit because it's not mathematically correct. It's x equals 3 and x equals -2. So how many x-intercepts do we have? 2. 3, 0 and -2, 0. But this 0 has a multiplicity of what?
4.
No, 4. Because of the other one.
It's 3 times here and then another time here, so it's the multiplicity of 4. It's happening 4 times.
Makes sense.
X equals -2 has a multiplicity of 2. Say again, Madison?
Why do you just
Because I want you to recognize that if it happens again at the end, you would have to count it again. Could you rewrite this as x minus 3 to the 4th times x plus 2 squared?
Yes.
Heck yeah. But would you have had this discussion and recognize that if it repeats at the end, that you'd have to count it again?
Nope, we would not have this. We wouldn't have this discussion.
You wouldn't have had a discussion. Also, Madison, who knows what's on the test, you or me?
Mr. Kenny,
Okay.
not you. So,
Can anyone else explain to me why I bring up that I know it's on the test?
because
you're
you're
trying to
doing
know
this to
the
help us.
So what's the implication there?
This is gonna go to the test.
Something that's similar to that might be on the test. It's like, I'm continuing. All right, number 5. All right, so a lot of us had questions about 5. I think the majority of them were from the graphing at the end, but let's quickly start here. Write the dilation of f of x as g of x. What operation goes with the dilation? Multiplication. Well, that's how we multiply, right? But a dilation means multiply. Ooh, that's more than I missed to show right away. Now, so that means g of x is equal to what?
It's plus 4.
Ooh, be careful, that's
I
a
mean,
negative
Negative
x
x
yeah.
plus 4, x
Negative
plus
plus
2,
4, x plus 2.
a times 3x minus 6.
Now, I will point this out. That's not where I would have started. I would have started by showing f of x dilated by 3x minus 6. Right? Owen, write the dilation of f of x. Dilate f of x by 3x minus 6. That multiplication is a dilation. So I take f of x and I multiply it by 3x minus 6, right?
Yeah.
Okay, and what is f of x equal to?
That.
Negative.
So I would have started here and then substituted this in for f of x because they are equal.
Okay, my brain just didn't. Okay.
I went with what y'all told me first, but I'm making a note of this is where I would have started. This would be my step 1 to get to this step 2 because f of x is equal to that. Right? I'm literally showing that I'm dilating f of x by the 3x minus 6. You good?
Yeah, I just didn't.
I would like that.
I am so.
I wasn't there.
Never mind, I see what you did, because that's what I did.
Oh, wow. Listen, Kenny, what is that laugh?
So, in part B, I asked you to convert g of x. Notice I even gave you a huge hint. It's in what form?
Factor.
And I wanted,
Standard.
so what do you need to do?
The area model.
Well,
Multiply.
or you need to multiply.
With the box.
So you either use the area model or you distribute.
Right.
I did the distribution method. Let's look at the area together. Do not forget, and this is a critical detail, how many factors can you multiply at a time? 2. Only 2. You can only multiply 2 at a time. So what I have is 3x minus 6 times negative x plus 4 times x plus 2. Does it matter which 2?
No.
I usually just start at the beginning. So I'm going to use that area model again. I'm multiplying. I've got 3x minus 6, negative x plus 4.
It's supposed to be square, right?
What? That's a good question. Remember, these are being added, right? So what this means is I have 6 x's being added, then I add 12 more x's. So it's just 18 x's being repeatedly added. But it's still a good question, right?
So this will be in with?
No. Because remember, that's only multiplying the first 2 factors. Notice I'm showing that this is still being multiplied by x plus 2. And so I'd have to do a second area model if that's the method I'm going with. So, what was this function g of x? So g of x, and remember this is a function, y'all, so write it that way. Negative 3x cubed plus 12x squared plus 12x minus 48. Is that what I got?
Wait,
So, again,
no, it's not what I got.
I mean, it may not be what you got, that's definitely what I got.
I multiplied when I did the like term.
Don't do that. Because remember, once you have everything inside of the area model, you're adding all those terms. Don't forget that. You're multiplying the row and column, but you're adding those like terms. Okay? So make sure you note that you're adding those like terms.
You took your son trick or treat?
My 2-week old.
Huh?
My 2-week old, 2.5-week old, who has no vaccine shots yet,
Yes.
who was asleep at 6 o'clock.
You would have all the candy. I would have given him some candy.
Oh, whatever.
How you gonna eat the candy?
Well, he has to.
Just a few days.
Can't eat solid foods until later.
I
You let him miss his first Halloween?
Right, he was just born like yesterday. Now
You
he
let him miss his
he
first
supposed to have
Halloween?
fun as soon as he fresh out of the womb.
Alicia, what were you asking?
If they were scared the first
I would
week,
take that man to a Halloween party. He would have got all of it.
Well, I'm glad you don't have a 2.5-week-old then.
It's because Selena
Alicia, what are you asking?
being occupied somewhere.
That's because.
Okay. When I have you all start working in small groups, remind me and I'll look for it,
You
okay?
gonna let me babysit?
That is a bad
It's
idea.
for free. You don't have to pay me. Just give me 100 on all our, all our assignments and stuff.
You gotta earn that crap. Alright,
By your child.
so part C was identify the zeros, because here's the fact of the matter is you need your zeros to be able to graph this. What should I do? What should I be looking at to determine the zeros? I need to look at the factors. What about them? Okay, well, so in order to use the zero products property, it has to equal what?
0.
Right?
Oh,
Identify the zeros when y equals 0. So 0 is equal to, notice how I set it equal to the factored form. Because I can't do that with standard form, but when I have factored form, I can use what property?
0 product.
Zero product property. There's my roots. Right? When I'm trying to find zeros, I want to use that zero product property, so I set my factored form equal to 0.
Yeah, I cracked it.
Okay?
How you do the second one if the x negative?
Say again.
How you do the second one, yeah, if the x negative?
It doesn't change how you solve it. What would you do to solve this equation? Negative x plus 4 is equal to 0. What would you do?
Actually, wrong number. I mean subtract.
Subtract 4. Alright, so negative x is equal to negative 4.
How you say, none of y'all see how you do that.
So either multiply or divide by a negative 1. Won't that make it positive? So x is equal to 4. Which is what I have right here. Right? This is the same thing as here though, Malaysia, right? 3x minus 6 is equal to 0. I add 6. 3x is equal to 6, so I multiply by 1/3. And x is equal to 2. Okay? Questions through those x-intercepts? Now, the next thing, the final thing, and it won't help you a ton to graph all of these individual details. The big thing is look at the big picture. One, what did I graph to actually help me get my polynomial function?
The point,
What are these right here?
Lines.
The lines.
Linear factors.
Linear factors. Remember, when I say that I have 3x minus 6 times negative x plus 4 times x plus 2, I'm multiplying those linear factors. I'm looking at y equals 3x minus 6, y equals negative x plus 4, and y equals x plus 2. I just graph those lines. That's it. right? If you look here at these notes, whoops, use 0/x-intercepts as changes from positive to negative. Never mind, not make the note about graphing the line, sorry. But you have to graph those linear factors, that's it. And notice every single x-intercept will match the zeros that we already identified. I have my x-axis, I have my y-axis. I just graph those linear factors. Now, what form of a line is each of these equations? Slope, intercept. So, hey, you can use slope intercept if you want to graph the lines. That's exactly what I did. A slope of 3 is 3 divided by 1, so I rise 3, go to the right 1. Y-intercept of negative 6. Y-intercept of 0, 4, slope of negative 1. But what is another mathematical representation that you can use if you're not comfortable just using slope-intercept form?
Point slope.
What's another mathematical representation? A table, right?
Oh, snap.
Guys, you can always use a table. I select the independent variable, the x's, and I just substitute them in. What's 3 times negative 2?
3 times negative 2 is negative 6.
And then negative 6 minus 6 gives me negative.
Oh, snap.
Substitute negative 1 in. What's 3 times negative 1?
Negative 3
Negative 3 minus 6.
equals negative 6. No, negative 9.
Dude, you should.
I substitute 0 in. What's 3 times 0?
0.
0 minus 6.
It's negative 6.
You should already notice a pattern. What's repeatedly happening?
Subtracting 3.
Add
3. Yeah.
So funny, isn't it? Snap.
But you can always make a table and then just graph those points. If you're struggling with graphing a line, create a table. But hopefully we know how to graph a line from slope-intercept. If you don't, might be a good thing for you to come into tutoring. Like, that's a skill that, and I know that I can't always say this, and I know it's frustrating sometimes, but at the end of the day, do you know when you're supposed to learn how to graph from slope-intercept form?
6th grade.
Not 6th grade, not quite.
7th.
It's about 8th, 9th grade.
It was 8th grade. You're supposed to learn it in 8th grade. If we're still struggling with it, please come into tutoring so I can help you with it. But it was 8th grade that you're supposed to learn slope-intercept form. And then you solidify that in geometry and algebra 1.
I did learn that.
I know.
Because I had to teach that.
Okay. Now, please pay attention, right? Final details. Pay attention. Once you have them graphed, remember I go this just like the number 3 on the other side. I look at my zeros and I look at a positive, negative, negative. What's a positive times a negative times a negative? Positive. So this function was positive all the way to this 0. And then I have a positive times negative.
Negative.
So it goes into the negatives, but it's got to get back to that 0.
Right.
Right? And so I keep using that to figure out an approximation of that graph.
Dang, I look like you're moving on the balls.
I don't know how I
Because, hey guys, listen. A lot of us just assumed, because a lot of ours have done this, that it's going to start down here, go up, down, and then back up. I intentionally made this one so it did not do that because I wanted to see that you actually understood. Please note, what did I draw to know where it's positive and negative? Those factors. If you don't have the factors drawn, it's really hard to know what the graph's going to look like. If you don't have the factors drawn, it's hard to figure it out. We are going to learn more next unit to make it easier without having to draw the factors every time. But if you don't draw those factors, it's hard to know. Destiny. I use the slope. Right? Y-intercept at negative 6, slope of 3. So y-intercept at negative 6, rising 1, 2, 3 to the right 1. Rising 1, 2, 3 to the right 1. That's how I got this line. Negative x plus 4, the slope is negative 1, so I went to a y-intercept of 4. Slope of negative 1. Through that line. Y-intercept of 2. Slope of 1. Slope of 1 through that line. So I use my slope and y-intercept. But again, that's where if you're not comfortable identifying slope and y-intercept and using that to graph, either come into tutoring or just make a table. This table matches this function, this linear function right here. You choose your x values, you substitute them in, and get your y values out. But we gotta know how to graph. Now, I will say we're gonna have review over the rest of today and on Thursday. So you can ask, I can sit down and show you a little bit more one-on-one if you need help graphing lines. But that tutoring is important. All right. I'm debating if I want to do this. I do.
You don't.
Do you want to be prepared for the test? Okay. Before I go into this, this is on page 180 in the book. The graphing paper is going to help you with the review that I'm going to hand out in a second.
Wait, you want supposed to write notes on that?
Yes, we will.
You could, or draw graphs or something.
I have a little place in my hand.
Alright, hey listen. What I'm pulling up right now is some of the homework questions because we struggled like whoa on homework. Everybody, this is your notice. You didn't do well on the homework, you have a chance to revise and resubmit on Friday.
Ooh-wee. Thank you.
So, learn from your mistakes. I will point out lesson 2 homework, all of that is what we just covered, right? Lesson 2 homework, all that's what we just covered. What we're about to look at is a couple of details from number 3, or from lesson 3. This is the homework from page 165. So these are the homework problems on page 165. 2 quick things. One, y'all gotta start reading. You're supposed to do this right portion. What are the directions for this right portion?
Provide an example of each key term.
The only people I saw at which Miss Estel graphed or graded, scored some of these, and I scored some of them. The only ones I ever saw were people giving a really crappy definition. I almost said a different expression, but yeah, half butt definition. That is not what it asked for here, is it? Does it ask for a definition of these terms?
No.
No, it asks for an example, which should include a definition, but, I mean, you could have just done one problem, one drawing that tackled all 3 of these. What's a cubic function? Like, in general, what could it look like?
You just draw, yeah,
I'll just squeeze it out.
like what we just did, yeah.
All those were cubics, right?
Yeah.
That's an example of number 3. I would add more detail to that. What makes a cubic a cubic?
You have a relative minimum and a maximum, and it varies like
Has 3 x-intercepts.
yeah.
Does it have to have 3 x-intercepts?
You can have 2.
It could have 2. It could also have
Has
1.
3 zeros.
Has 3 zeros, right? Because at what degree is it? Third degree polynomial. So it has how many zeros?
3.
But remember, some of them could be imaginary, some of them could have multiplicities. So it doesn't have to have 3 x-intercepts. This one does, but it doesn't have to have 3 x-intercepts. It has to have 3 zeros. So there's an example of a cubic. Anyone see an example of a relative minimum?
Yeah. The bottom part of the curve.
Second one.